My name is Arfi Matlub, and the topic of my presentation is a smart framework to detect threats and protect data from IoT based on machine learning. So basically, this work proposes a powerful solution to address modern cybersecurity threats in the IoT systems using a hybrid ML machine learning and deep learning in the fog computing architecture. So basically, the agenda of the uh, presentation is that I'll be covering the introduction and with the real-time applications of it, and I'll explain the literature review and the problem statements of it, and then I will briefly explain the proposed solution that is being covered and included in the research paper. Then I'll compare the results of the different models, and then I'll explain the conclusion and the recommendations and my future recommendations and suggestions. So, so the introduction includes that the IoT connects billions of devices using the WSNs and the RFID tags for the data collection and communication. And the security threats in the IoT includes eavesdropping, tampering, and the DOS attacks. CIA, which means confidentiality, integrity, and availability, is the core of the IoT security. Traditional methods struggle to scale with the modern dynamic IoT environments. And the literature review includes that the prior research used various techniques. For example, the blockchain-based trust models work well, but lacked machine learning capabilities. Some studies show that the CNN and the RF models performing very well on the IoT datasets like NSL and the KDD and the IoT-23. However, few integrated real-time responses or the cloud computing. So the CNN for the intrusion detection, NSL, and the KDD focused on the protocol and the service type features that the CNN model achieved 99.3% accuracy, showcasing its efficiency for the cyber attack detection. Machine learning for the borderline attack detection, which is the bot IoT, used a machine learning model on the IoT-23 and the bot IoT datasets to detect denial of service attacks. RF and the XGBoost achieved near 99.8% accuracy, which is nearly perfect, and it has good a lot of good impact on it. The benchmark study in the machine learning for the IoT is that they compared RF, SVM, and the deep learning model for the attack classification. RF showed consistent superiority, and especially in the binary classification due to its assembled nature. So the problem statement includes that the IoT lacks strong real-time threat detection at the sensing layer where the attacks often originate but go unnoticed due to limited local processing power and the resources. Existing machine learning models trained on specific datasets often fail to generalize across varied IoT environments, leading to low accuracy in detecting unseen attacks. Moreover, these models suffer from the data imbalance where benign data dominates causing poor detection of rare but critical threats. Blockchain, while secure, introduces latency and the computational overhead, making it impractical for the real-time or time-sensitive applications such as live monitoring and immediate threat mitigation. So that the blockchain is taking too much computation overhead, too much computation power, and it becomes impractical and impossible for the real-time and time-sensitive applications. And also, the many traditional methods focus on detecting threats post-compromise rather than proactive detection, leaving critical gaps in defense. And the privacy concerns are often overlooked with insufficient mechanisms to detect tracking and profiling and or identity-based threats on the in IoT system. So, basis on all, so keeping in mind all the problem statements on this research paper, we propose a solution that the it introduces a hybrid framework that integrates machine learning, deep learning, blockchain technology, and the fog computing to enhance the security in the IoT systems. At the core is a multi-layered architecture where sensor data is first processed in the fog layer. Two additional features, value difference and delay time between the readings, are computed to capture abnormal behaviors. So the fog layer pre-processes data to reduce redundancy and noise, enabling efficient local classification using the trained machine learning model using the KNN, SVM, reinforced logistic regression, and the deep learning based ANN model. And each model classifies the incoming data independently, and a voting mechanism is used to finalize the decision. If a majority of the models detect a threat, system responds accordingly. Simultaneously, the blockchain component secures data records and enables audit trials, making the system tamper resistant, and ensuring the data integrity. This design supports the real-time threat detection at the edge while minimizing latency and reducing the cloud load, making the framework suitable for the large-scale and delay-sensitive IoT environments. So our proposed solution not just solves the problem and includes a new feature, but it also makes it more efficient and it reduces the load and also minimizes the latency and the interaction reaction rate. So the diagrams in the flow chart, which is of the system with how the system works, shows it how IoT data is monitored and analyzed before being processed by a machine learning and a deep learning framework. It interacts with the fog computing layer with a fast edge level decisions, classifies threat using the machine learning models, and securely stores the results. This flow ensures that a real-time threat detection, low latency, and the secure logging. So as you can see that there's a diagram that it first monitor IoT environments, then analyze IoT data, then the machine learning and the deep learning based framework using the process and send the data, process data to the fog computing framework, and then from the fog computing, we have a detect threat that has been sent into the to classified with the machine learning ORL, which is then stored as a classified threat. So the monitor IoT environments collects real-time data from the various IoT devices like sensors, cameras, and smart applications, and then analyze the IoT data used by pre-processing the data, adds delays and value inferences, features to enhance the detection accuracy. And then the machine learning and the deep learning based framework applies machine learning and deep learning models to identify the patterns or the anomalies in the data. And the fog computing handles the quick and local analysis and decision making near the data resources to reduce latency. And the classifying with machine learning, the deep learning is that the final decision model using the final decision is being made using ensemble voting from the different models to determine if it's a threat or not. Then we have to store if it's a threat. Then we store that the classified threat logs detecting threats securely, typically into a blockchain or tamper-proof storage for auditing. The result of the proposed solution is that the proposed framework was tested using the TUN IoT dataset enhanced with delay and the value chain features among several machine learning models. ANN achieved the highest performance with the 99% accuracy. The use of SMOTE improved class balance, boosting overall detection rates, and the framework efficiently identified multiple attack types such as denial of service attack, tampering, and the injection, showing strong precision, recall, and the FN scores, especially with the ANN. And the results were obtained using the TN IoT dataset, which was augmented by the two additional features: the time delay between the sensor readings and the rate of change in sensed values. These enhancements significantly improved the model's ability to detect abnormal behavior indicative of threats. Initial testing with the traditional machine learning models, such as k-nearest neighbors, support vector machines, and the logistic regressions, and the random forest, showed that the RF achieved the highest performance among them with the 94% accuracy, which means that the reinforced model was the motivator selected and showed the most accuracy on it. To address the class imbalance issue, where the non-malicious data heavily outweighed attack data, and the synthetic minority oversampling technique method was applied. This resulted in more balanced classes and improved accuracy to even 95%. So a deep learning model using the ANN, which is the artificial neural networks, was then implemented and trained on the balanced dataset. It achieved an outstanding accuracy of 99%. Additional evaluation metrics confirmed that the deep learning model's superiority. ANN achieved a high precision of 99.8%, a recall of 98.3%, and the FN score indicating a strong ability to correctly identify threats while minimizing the false positives and the false negatives. The models effectively identified different types of attacks, including tempered data, injection denial of service, and the backdoor threats. Visual comparisons and confusion metrics validated these results across all the models.